All right, we're going now. Okay. Yep, that's just gonna be good enough. All right, so again, if you need chapter 3 notes or homework, they're right up there on that front desk. G period, I'll have some on my desk if you need them tomorrow or today for you. Let's do a quick little review of what we've done already in chapter 3. I would love to finish 3.1. If I can get into 3.2, that would be great. I'm just gonna do as much of this as I can right now. Reminder that we are going to have a quiz sometime after Thanksgiving, and then we will have a test regardless of where we are in chapter 3 on December 7th. If we need to finish learning any stuff, we will do that between then and the final, but there'll be no more quiz or test between December 7th and the final exam. Cool, so you have 2 more assessments, a quiz and a test. After the week after Thanksgiving. I'll put it on Schoology so you guys know. I'll update that this weekend, but in my head I've been thinking sometime that week we'll do a quiz, and then December 7th, no matter where we're in chapter 3 with the test. And like all tests, we'll do a review day before that. So but you guys were here when we did chapter 3. I did it before our test though, so let me just review a couple things. I'll just leave the notes up. I'll just kind of walk through a few things that we talked about, and then we'll continue on with this stuff. So chapter 3 is our exponential logarithmic chapter. The very first thing we talked about was the idea of a power function versus an exponential function. And the biggest thing I want you to know is that an exponential function has x as the exponent. So most of what we're doing in this chapter, x is the exponent. When we got to number 2, we had x as the exponent and we plugged different exponents in. And so we practiced certain special cases. So like the first thing we practiced was plugging 0 in. Remember, if you plug 0 in as an exponent, anything to the 0 power is the same thing as 1. When we had a negative exponent, that makes it a fraction. So instead of 3 to the negative second, it becomes 1 over 3 squared. You essentially flip it. And then the last thing, I already have it highlighted in that blue and pink color, is the exponent that's a fraction. Remember, if the exponent's a fraction, it becomes a radical. So 3 to the 1/3 becomes cube root of 3. 4 to the negative 3/2 becomes square root of 4 to the 3rd power. So we reviewed that the other day. Another thing we did, this was the last problem we did in class, and then I kind of intentionally left this other one so as for us to review again today, is we were writing the equation of an exponential function. In G period, I talked about, like, we've learned a lot of different equations of functions. So like we learned back in algebra 1, the idea of a line function. A linear function is y equals mx plus b, right? We did review that in pre-cal at some point, but like you've been doing that since algebra 1. One thing we learned this year, and I don't remember if you learned in algebra 2, but the equation of a quadratic, y equals a times x minus h squared plus k. One thing I don't think you've ever learned that we're doing for the first time here is my exponential function. So if you don't have this written down, I would make sure this is written down somewhere. Y equals a times b raised to the x. So if I say write the exponential function of blah, 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 we're going to use this form, y equals a times b raised to the x. I have to give you, I guess I don't have to, but the easiest way is if I give you a point that has a 0 in it. So I wrote it in function notation, f of 0 equals 3/2. That's the same thing as 0, 3/2. And then my other point was f of -2 equals 108. And that's the same thing as -2, 108. So we got to remember how to go from function notation into coordinate points. And then we use those coordinate points. We plug in the first point 0, 3/2 into my general equation. And then we got what a was. Once I got that a value, then I plugged a and then the second point in, and then I was able to solve for what b was. My very final equation still has x and y in it, but we were able to put a and b in as well. So again, it's a general form, y equals a times b raised to the x. That's what it looks like right here. One thing I know I kind of moved really quickly through with you guys was this very last part of the equation. We had b squared equals 1/72, and I think I really rushed through it at the end. We square root both sides, And I know that you learned how to simplify radicals, but I'll just talk you through it again because I really need us to know how to do this. When I have square root of 1/72, I'm going to start breaking that down. The first thing I do is look at the top and look at the bottom. The top square root of 1, well, the square root of 1 is just 1. And then the square root of 72, we're actually going to have to simplify that down. I made a little factor tree off to the side over here. Bless you. Square root of 72 becomes 6√2. And then the very last step I need to do is I cannot have any radicals in the denominator, so I multiply by √2 on top and bottom. The top just becomes radical 2, the bottom becomes 6 times 2, which is 12. We're going to practice these kind of skills later on, but I just want to make sure that we looked at that. Is everybody okay with what this is so far? Okay, perfect. So that was our little review, and now we're just going to keep moving forward. The next problem is just like the one we ended with last class, so we're going to do this one together. Remember, we've got our coordinate points. 0, 3 is my first coordinate point. F of 0 equals 3, that's my first one. My second one is 2, 6. So I've got 0, 3, and 2, 6. Remember, we're still going to use the function that, or the formula that I have highlighted, y equals a times bx. And we're going to plug in for that. I like to start with my 0 and my 3. So I'm going to say 3 equals a times b raised to the 0. I like to put that little dot for multiply, but sometimes that screws you guys up. So you can think of it as like parentheses. You can just think of them next to each other, whatever makes you the most happy. Just know that they're being multiplied together. But b to the 0 is 1. So that crosses out. And so I just get 3 equals x. Oh, nice. That's easy. The first equation always just gives me a. Bless you. Now I'm going to plug a and then my other x and y point in again to my formula to get b. So now I'm going to use 2 and 6 as my x and y. Bless you. 6 equals 3 because that's a times b to the second power. This one, maybe it's even better not to have that multiply because 3b squared, that looks like something we've seen before, right? Let me write it closer. A is 3, b is b, we don't know what b is, and then x is 2. Now we can just solve this pretty simply, right? What would I do first? Divide by 3. 2 equals b squared. And then what would I do to get b all by itself? Square root. B equals radical 2. Now, I know we just spent a lot of time saying every time we square root something, we got to make it a plus or minus. When we're doing this form, I just want it to stay positive. So just keep it at positive √2. There's no need to make it plus or minus because if I put it back in that formula, if I think of it as y equals 3√2x, I don't want to say plus or minus √2x. Yeah, Hunter.
So in part of that, you always take b to the 0.
Well, I have to give you this point, but yes, always do the 0 power first. Great question. All right, cool. Ready to keep going? All right. The next one is talking about transformations. We have done transformations in the past. This is kind of going back to chapter 1. So we're using this basic graph. Yeah.
Are we supposed to figure out what A and B are plug it back in?
I would plug it back in, see how I ended like this. Yeah, I would plug it all the way back in. And if this is ugly to you, you can always put parentheses around your radical 2 to make sure he stays on the inside. All right, as I'm looking at the next one, I'm looking at transformations of this graph. So it says f of x equals 2 raised to the x. We did one of these with our BFFs. Do you remember our exponential graph for our BFF was something like y equals e to the x? Do any of you remember what that graph looked like? Yep, I see a lot of like hand signals. It looks something like this. It started low and then it went high. It started at the point 0, 1. That's the one I always told you guys. We don't need to worry about that here because we're doing a base of 2x and it will not go through that point, but it looks something like this. Mine looks a little curved. Let me straighten them out. So it just goes up exponentially. That's what we're doing here, but now we're gonna have transformation, so you're gonna have to help me remember, does something move my graph up and down? Does it move it left and right? Does it flip it? All of that fun stuff. So if I look at this first one, what is this -3 attached to the X do to my graph? That's if it's multiplied. If it's minus, think about this as being like in parentheses with the X. To the right 3, very good. This is gonna move it to the right 3. Since it's being added or subtracted, it's gonna move it left and right, and it's opposite of what we think, so it's gonna be moved to the right 3. So we're essentially going to the right 3, and it'll be about here. So it's gonna be a little bit flat, a little bit longer, and then it's gonna exponentially increase up. And again, I'm just sketching it, nothing super exact. All right, the next one, I was starting with 2 raised to the X, and now I've got 2 raised to the -X. Do you remember what that negative does to my graph? Flips it. Now, does it flip it over the X? Does it flip it on top of each other, or does it flip it left and right? It's actually gonna go left and right. On top of each other as if it's out front like that, which is actually the negative that we're more used to. This is the negative we see more often where it flips on top of each other. This one's gonna flip it like left and right. So instead of, don't write this one, instead of having it go like this, we're gonna have it flipped opposite. It's going to start high and then get much lower like that. So I'm gonna say flip over my y-axis. Flip over my y-axis. Okay. Great job. Go ahead and flip your paper over or scroll down if you are. Oh shoot, the next one's leading us right up to where we were just at. What did you just tell me we were gonna do?
Flip it.
Flip it like over the x-axis. Good, so that's what we're gonna do. If this is what my original graph looks like, we're gonna flip it down like this. Mike, I'll move all those papers, I'm so sorry. Do you need those? I'll take the rest of them. Good, so this one flips it over the x-axis.
Wait.
What's that? Uh-huh. Do you want me to zoom in more? Is that good enough?
Yeah.
Good. Thank you.
Wait, so we look, all right, so go up to it. And, for like these, we're going up to the y-axis.
Are you talking about letter D that we haven't done dog?
No, not these.
Oh, B.
Like, how it's like up on the y-axis.
So the up one on the y-axis is just like the parent graph. So if you remember back when we did our like BFF graphs, y equals e raised to the x. It had a point that always went through the point 0, 1. So it's always up 1 on the x-axis. Which actually makes sense, right? Because if we have anything e or even 2 raised to the 0 power, what answer should we get? 1. So either way, we'll have that point there on 0, 1. So that's kind of the only point I'm moving. I don't know what any of the other points are. I could figure it out, but it would just be a lot more work. I know that point easily. All right, last one, D. There's actually a couple things happening here. First thing is this +1. What do you think that +1 does to my graph? Moves it up 1. Good. So instead of going through the point 0, 1, it's going to go through the point 0, 2. Now, if you notice, all my other graphs were 2 to the x, and this one is 0.5 to the x. Can we manipulate that so it becomes 2 to the x? So 0.5 to the x is the same thing. What is that as a fraction? 1/2, good. So if that's 1/2 x, how do I change that so it becomes 2 raised to some power? Not, what exponent could I use to change it? Not -2, I like the idea of a negative. -1, right? So remember a negative exponent flips it. It makes it go into a fraction. So 2 to the -1, that's the same thing as 1/2, right? So think of this as 2 to the -1 raised to the x, which is just 2 to the -x. So the 0.5 raised to the x is the same thing as 2 to the -x, which, oh, we've already done that. What happened when we had 2 to the -x? Flip over my y-axis, it flips like this. Flip over y-axis. So instead of starting low and then going high, it's going to start high and go low. Now notice that I didn't go all the way to 0. Since I moved up 1 unit, normally it never crosses the x-axis, right? Now if I move up 1, what is it never gonna cross? 1. So I essentially have a little asymptote here at 1. We did not draw it on the other ones because it was kind of assumed. We knew that's what our paragraph looked like, but we could go back and draw a little asymptote on our 0 line if we wanted to on all of these. Good, that was just a little transformations to kind of understand what's going on with these graphs. All right, can we keep going? Okay. Number 5 says state whether f of x represents growth or decay, describe its end behavior. We're gonna do end behavior in limit form. Do you remember how we looked at limit form very briefly in the last unit? Limit notation looks something like this. It says LIM limit of f of x equals, and we're gonna say some answer. And underneath that limit, it says X arrow, and then it either says positive infinity or it says negative. So we're gonna do 2 of these for each of them. We're gonna talk about what happens as we approach positive infinity, and we're gonna talk about what happens when we approach negative infinity. The reason we just did our graphs is so that now we have a little idea of what's going on here. All right, 3 raised to the x. I know that it's now a 3 on the graphs we were just looking at or a 2, but this 3 doesn't change anything about my graph and how it looks. So this graph is still gonna look like we're going from low to high. Would you think, if you, knowing nothing, were to describe that, would you call that growth or decay? Growth, right? It looks like it's getting bigger as we go over time, so we're gonna call that growth. Should we do all the growth and decays and then do limits, or do you want to do the limit for each one and then do growth and decay? Does it really matter to any of you? Okay. Let's actually label growth and decay first, and then we'll come back and do the limits because we'll have little graphs for all of them. So let's look at the next one. Next one is 3 to the negative x. What did we say that negative x does to my graph? Good, flips it where? Over the y, good. So it flips it. So instead of starting low and ending high, it's gonna start high and end low. What would you think that is? Decay. So we read our graphs kind of from that left to right. So this is decay as we go across the page. All right, this 1/2 raised to the x is a little confusing. It's kind of like that one we just did on our transformations. Remember how we were looking at all the 2 raised to the x and then we had that 0.5, and we said that was a lot like having an x to the negative power. This is going to be flipped like the one above. This is a lot like 2 to the negative x. So it is also a backwards graph. It is also a decay graph. Damn, you well done. Let me write you with a note. I'll send him an email, but I didn't yet. So let me write you a note. Great, and then now I can't. He makes fun of this jig cast. Oh, I'm so sorry.
Thank you.
I have another one of these little fractions in here, or decimals, I guess you can think of it as. But this time the decimal is getting raised to the negative power, so we can think that that's like a normal graph. Because essentially, I know that 0.75 is like 3/4. It would be the whole number, or the number greater than 0 would be 4/3 to the negative, but it's already being raised to the negative x. So essentially those negatives cross out and it's a positive. I know that's kind of confusing. What I want you to know from that is the fraction and the negative cancel each other out, and it is a normal growth graph. So kind of some things to kind of note. If you have a number bigger than 1 with a positive exponent, or a fraction, a decimal with a negative exponent, those are both growth. If you have a whole number with, let me do red. If you have a whole number with a negative exponent, or just a fraction or a decimal, those are decay graphs. This is helpful to have done this first, because now we're going to do the limits, and we'll do the limits of both the growth ones first. Let me draw some like little lines so I can kind of keep this neat. I will tell you, limit notation is not huge to me in pre-cal. The reason I show you limit notation is because if you take calculus, I want you to have seen it before. My goal is for you to not like to leave this class not having seen stuff. So this is not necessarily something I'm going to be stressing a lot or testing you on necessarily, but it's something that like I want you to have seen. So, okay, so I have kind of two columns here because we're going to do the limit of my function as x approaches positive infinity, and the limit of my function as x approaches negative infinity. I'm glad that we drew those little sketches because those are going to be helpful as we determine the limit. Remember, the limit is like our end behavior. So it's like in the past, we wrote it like as x approaches positive infinity, y approaches something. You guys remember that, right? This is just a fancier version of this. So I'm going to go back to my graph. The first one I'm going to do as x approaches positive infinity. So I'm thinking about as x is getting bigger and bigger, what's my graph doing? As x is getting bigger and bigger, what is this first graph doing? It's going up, right? It's going up to infinity. So my limit of my function as x approaches positive infinity is also positive infinity because my y is getting bigger and bigger and bigger. I like to put a positive sign in front of my infinity. You don't need to. As long as you have a negative in front of your negative infinity, I do not care. I just personally like positive infinity with a positive sign. Similarly, I'm going back to my graph for a second. What is my limit as x approaches negative infinity? What is y getting closer and closer to? 0. Very good. It will never ever cross 0, so it's going to approach 0. This is the same thing for letter D. Since it's also a growth function, it looks just like letter A, right? So its limits are going to be the exact same. My limit of my function as x approaches positive infinity is still positive infinity. And then my limit of my function as x approaches negative infinity is still 0. Just like the other growth function. So all growth functions, their end behavior is the same. Their middle might look a little bit different. It might be a little fatter, it might be a little skinnier, but as you approach like the polar ends, it will be 0 or be positive infinity. All right. The last two are my decay function. So let me set it up with my limit. So I'm going to write limit of my function as x approaches positive infinity for both of them. And limit of my function as x approaches negative infinity for both of them as well. I'll zoom out. I will tell you it's different than my growth ones because it's decay, it's essentially backwards. Let's go look at our pictures. My decay graphs are the same, but as x approaches positive infinity, what is my y approaching?
0.
0, good. And then while we're looking at the graph, as x approaches negative infinity, what's my graph approaching? Positive infinity, it's still going up, right? We wanna know what my y is doing. My y is getting bigger and bigger as my x is getting more negative. So as my x gets more positive, I get closer and closer to 0. I will never cross the 0 line. And then as x gets smaller and smaller, I'm going this way, my function is getting bigger and bigger. So positive infinity is 0 for both of my decay functions, and for my decay, as we approach negative infinity, it's positive. And so those are essentially backwards of each other. Let's scroll down to number 6. Now, do these look like the functions we've been dealing with? No, do you remember what these are called? These were one of our BFFs. Or similar to one of our BFFs. These are the really funny ones that I'm sure you spent a lot of time trying to study. These are the logistic functions. These are logistic functions. If you remember what the logistic function looked like, it's something like this. It looked kind of like an S. It started like around 0, and then it went up to about 1, and then or about 0.5, and then it went through. It had like a boundedness on top, and it was bounded above at 1 and below at 0. So we have 2 horizontal asymptotes here that this graph is kind of constrained between. I'm going to tell you that one of those horizontal asymptotes will always be 0. The other horizontal asymptote is going to be whatever is in the numerator. Another word that we use for that is a limit to growth. So whatever is in the numerator is your limit to growth, or one of your horizontal asymptotes. So this problem says find the y-intercept and the horizontal asymptotes. Well, the horizontal asymptotes are super easy to find. Do you guys need something?
I mean, we're doing like a broadcasting class commercial. We need to introduce like 2 people for like 1 minute. Yeah.
Okay, that's fine. Does anyone want to be in the commercial?
All right. All right. I was proud.
Sorry. That's so strange. They were just standing at the door looking in. Oh, sweet boys. All right, so my horizontal asymptotes are always going to be at 0, and then whatever your numerator is. So in this first one, it's 0 and 12. In my second one, it's going to be 0 and 18, and then the last one is going to be 0 and 9. Okay. Remember that horizontal lines are always y equals, so that's why all my horizontal asymptotes are y equals. It just tells me that they're going to be horizontal lines. Now I'm going to do my y-intercepts. How would I find a y-intercept? Put 0 in for all my x's. So I'm going to put 0 in for all of my x's. I've got y equals 12 over 1 plus 2 times 0.8 raised to the 0. Oh, should I get my calculator out to do 0.8 to the 0? No, what is that? 1. 2 times 1 is just 2, so this is like 12 over 3, which is 4. Can I be quiet for a minute? Can you do the other 2 y-intercepts without me? Just plug in 0. What's up?
Does it always have to be 0?
In order to be a y-intercept, yes.
So you always.
These are logistic functions and they will always have two horizontal asymptotes. One will always be 0 and then the other one is just whatever the numerator is.
So when you goes 5 or 7 0 powers.
Always 1, no matter what it is. So that 0.2 becomes 1, so then 5 times 1 is just 5. So 18 over 1 plus 5 is 6, so that's gonna be 3. You know. Plus 2. E raised to the -0. Well, -0 is still 0. E to or 0 to any power is still 1. So even though that looked a little scary for a second, it's still just gonna work out to be a really nice, pretty number. Cool. Flip your paper. We had a few word problems. Sorry, yeah, am I moving too fast? Horizontal asymptotes are always 0. And then whatever the numerator is here. So these are called logistic functions, and just by definition of a logistic function, one of their horizontal asymptotes is 0, the other one is whatever the numerator is. Yep. 0.
So it would be -0.
Yep.
But then that would still.
That's still, yep, -0 is still 0, anything to the 0 power is still 1. So I know it feels scary for a second, but at the end of the day, it's still just gonna be 1.
And E is staying.
Well, anything to the 0 power is 1. So e to the 0 power is still 1. Doesn't matter. We're gonna deal with e's later. There's a special button on your calculator. Have you guys done e's before? Yes, no, maybe. Okay, no one seems to be like definitive, so I'll explain those more later. E's a special number, kind of like pi, and it's special with our exponential, so we'll get to it as we go. But we're gonna do a few word problems here. 7a says bacteria growth. The number B of bacteria in a petri dish culture after T hours is given by this. Oh, thank goodness. On all of these examples, they give us the equation. Later on, we'll have to write our equation, but right now they're giving us the equation, which is awesome. B equals 100 E raised to the 0.693 T. Okay. The first question says, what was the initial amount of bacteria present? So that's at when time is what? 0. So if we want to know the initial, that's when time is 0. So we're going to plug 0 in for T and see what we get out. Bacteria equals 100 times E raised to the 0.693 times 0. Well, 0.693 times 0 is still 0. And E to the 0 is 1. So all of that's going to cancel. So my initial amount of bacteria is 100. All right, letter B says how many bacteria are present after 6 hours? What do you think I should do to find that? Good, plug in 6 for T. Now we're plugging an actual number in for T, so we are going to need our calculator. So I'm going to go ahead and get my calculator next to me. Don't need it that big though. Let me write my equation first. B equals 100 times E to the 0.693 times 6. I grew up with an old calculator, so I'm super careful. I just like to do everything in parts. I'm personally going to do 0.693 times 6. And then I'm going to take that number and then raise it to the E, and I'm going to take that number and multiply it by 100. You're welcome to put it all in at once. I just was afraid of like parentheses and messing something up. So I like to do it in parts. E on the calculator, if you press second and then the division sign. if you look at your calculator, look at the division sign, see how it has a little blue E on top? So I press the blue button second, I press division, I get E. And then I can do caret and raise that to whatever power. There's actually another place where E is now that I say that. Another place you can find E that will always already be ready for an exponent, if you press second and go to LN, that's on your like left-hand column, second LN gives you E to a power, and then you can just type in that power. See how it's gonna give me the exact same answer. So it doesn't matter if you do second division or if you do second LN, it's all, both of them are there. And I wanna take that number and I wanna multiply that by 100. So I get bacteria is 6,394.4. Do I need 0.4 of a bacteria? No. When I'm talking about like living things like bacteria, humans, animals, I'm gonna round down because 0.4 of a bacteria is not quite a whole bacteria, but I can't have 0.4. So we'll keep it at 6,394 bacteria. If you wanted to plug it all in at once, I think you could. I would do 100 and then second LN and then 0.693 times 6. And I still get the same answer. So just be careful when you're plugging things in or not. All right, I've got another problem like this. Anybody questions on that first one? All we did was plug each other. All right, this next one's called carbon dating. It says the amount of C in grams of carbon-14 present in certain substances after T years is given by this. So this is our equation. Yay, they gave it to us again. All right, letter A says, what was the initial amount of carbon-14 present? How would I find that? Sydney? T equals 0. Okay, so I'm gonna plug T equals 0 in. C equals 20, E raised to the negative, oh, there's a lot of zeros there. 0.00012116 times 0. It doesn't matter how big or small that decimal is, anything times 0 is 0, anything raised to the 0 power is 1. So whatever that is, it all cancels out, and I just get C equals 20. So there's 20 grams of that carbon amount at the beginning. Now, letter B says how much is left after 10,400 years? And then it says, when will the amount left be 10 grams? Okay, we got essentially two problems in there. The first one says how many will be left after 10,400 years? What do I plug that in for? C or T? T for time, good. So time is about to be 10,400 years. Okay, let's do that and then we'll do the second part of point B. 20 e to the negative point. I count 1, 2, 3 zeros, 1, 2, 1, 6 times 10,400. Now there's so many zeros in here, you just got to be careful with when you plug it in. I'll try plugging it all in at once. I've got 20, and then I'm going to do second ln to get e to the power. And that's going to be negative 0.1230 zeros. 1216 times 10,400. I know those numbers are probably pretty small for you to see, but enter, and I get 5.6. Seems good. Since this is in terms of grams, I'm okay with it being a decimal, so 6.5 grams is something that you can measure. We're used to having grams or like things in terms of weight in decimals. That's okay for me. Okay. Now the other part of B said, when will the amount left be 10 grams? Okay, 10 grams, does that mean that the 10 goes in for the C or the T? The C, it's in terms of grams. So I'm gonna have 10, whole new problem, 10 equals all of that, 20e raised to the negative 0.00011216t, sorry. Okay. I will eventually teach you how to solve this by hand. We're not there yet. So what we are gonna do is my favorite thing, which is plugging it in the calculator. So we're gonna plug one of these in for y1, the other one in for y2, and we're gonna see where they cross each other. So y1, I'll just make that 10, y2, 20 times e, second ln raised to the negative 0.00011216 x. All right, let's see. Let's say my window is standard. I know that's not gonna work. Do you see like a tiny blue line at the very, very, very top? So that means I need to be a little bit higher. I already knew that though, if my y equals was already at 10, so I need to at least be at 10. It looked like there was nothing in the negative, so I don't need any negatives. We'll make all of those 0. 0. I need my max to be bigger than 10. Let's make it, my y max needs to be bigger than 10. Let's make it 100 just so I can see everything. I don't know what my God, I'm doing crazy stuff right there. I don't really know what my x max is gonna be. It looks like from previous experience, it's gonna be a very big number. So x max should probably be bigger than 10. I have the benefit of knowing what it will be, but let's go ahead graph really quick. So like if you didn't know what it was and you just kept it at 10, we would see. If I had no idea, I would say, okay, it looks like it's not touching yet. So it's gonna take a lot more for it to touch. And I actually am a little high on my y max. I don't need to be that high. Maybe we'll bring that down to 30. And then my x max, I'm just gonna tell you it's gonna be really big. Let's make it like 8,000. If you didn't know and had to guess, it might take you a little bit more time, but I believe we'll be able to see it from here. Graph. And there I see a nice little crossing path. If they equal each other, they have to cross at some point. So if you're playing around with your graph and you're like, they're not crossing, just make that x bigger or make that y bigger so you can see farther away. I care about where they intersect, so I'm gonna go second trace intersection. And I'm gonna go left bound. Where's my mouse? Every time I need my calculator, it decides it wants to not do what I want it to. Good, there's my intersection. 5,700.22, blah, blah, blah. I'm gonna round that up to the next full year, because if I keep it at 5,700, it won't yet reach 10 grams. So we're gonna round it up to 5,701 years is how long it takes. So T is equal to 5,701 years. Based on this equation, based on what's given to me, that is how many years it will take for there to be 10 grams left of this carbon. We got one more problem. Are you ready for this last problem? We can finish up with this. Okay, this last one, is this an exponential function or is it a logistic function? It's a logistic, good. How do we know it's a logistic and not exponential? Not necessarily. The last one had an E. It has a fraction. That's the biggest thing I care about. The fraction is different than the exponentials. Okay, so it says using 20th century US Census data, the population of New York State can be modeled by this, where P is the population in millions and T is the number of years since 1800. Based on this model, we want to answer these questions. Okay, what was the population of New York in 1850? One important thing I read from the beginning was T is the number of years since 1800. If I want to know what was the population in 1850, what should I plug in? For what? T equals 50. I don't want to actually plug in 1850 because the model starts at 800, which means 800 is 0, 801 is 1, blah, 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 850 is 50. All right, let's solve that. Gonna be a little calculator thing. I'm gonna plug 50 in for T. You can rewrite it if it makes you happy. If it doesn't, don't feel like you have to. 19.875 over 1 plus 57.993 e raised to the negative 0.035005 times 50. Woof, that was ugly. I'm gonna be honest, I'm too scared to plug that all in at once, so I'm gonna plug it in some pieces. I'll do e to the negative 0.035005 times 50. I'll do that first. Okay. And then I'll do 1 plus 57.993 times that number. Okay, that's the whole denominator, so then I'll do 19.875 divided by that number. And I get 1.79. And this is in terms of millions. So 1.79 million. Letter B says, what will New York State's population be in 2010? What should I plug in to figure out what the population should be in 2010? 210. Cool. Plug the same thing in for 210. So I'm essentially doing A, but I'm going to plug in 210 for 50. So go ahead and do that for letter B. Okay, do the same thing. I'll do it a little bit. Feeling a little ballsy, I'll go a little bit more. E raised to the negative. All right, when I plug this in, I got 19.162 million. Is everybody okay with that? Okay. That's a huge jump. I was just at, in 210 years, I went up, or I guess in, what is that, 160 years? I went up from 1.79 million to 19.162 million. The last thing says, what is New York's maximum sustainable population? That says its limit to growth. Remember logistics, I told you there's 2 horizontal asymptotes, one's at 0. Where's the other horizontal asymptote? The numerator. So whatever the numerator is the other asymptote, or in this case, another word we can use for it is the limit to growth. So the limit to growth, C, is going to be 19.875. So I had no work to do for that. The limit to growth is just the numerator. I'll get rid of the calculator, I don't need it anymore. So that is perfect timing. We are done with 3.1. So I need your 3.1 homework done for next class, which is Monday.
Yeah.
Yep. All right, let me turn this off.